Hello everyone. Today we're going to explore how recipes work. The Nexus recipe system lets you schedule commands. Commands chain together to describe a complete process. The most typical process is a sample growth recipe. In Nexus, there are two ways in which you can do that. In this video, we will focus on Classic, a straightforward scripting language for creating basic recipes with a well-defined command set. To hear more about Python, a more advanced way of doing recipes, for more complex materials and structures, please refer to our Nexus Python scripting video. Classic recipes are created and executed line by line. The most basic commands are open, close, and wait. These are used to create blocks of code that correspond to layers deposited on the sample. To make the relationship clear, a visualization appears on the right side to show you what the commands will do. For example, this sequence grows a 25 nanometer thick indium gallium arsenide layer. Unlike wait, the pause command lets you specify an indefinite wait. The ramp and set commands allow you to set individual values. Ramp allows you to set a target temperature and a ramp rate. Rather than spending the time calculating how long the ramp will take to complete, you can pair ramp with wait ramp end to wait until the ramp is complete and then continue executing the next line. Finally, the last recipe command, record BEP, records the beam equivalent pressure for automatic beam flux monitor calibrations, but we will discuss that in the upcoming BFM video. Now let's do an example together. For this example, we are going to assume that the arsenic and gallium flux calibrations have already been done. First, on line 6, we start the gallium 1 cell ramp, raising its temperature to 999 degrees Celsius at 1 degree per second. As you may know, gallium arsenide substrates start to thermically decompose above 400 degrees. On line 9, we set the sample heater to ramp to this safe limit at 1 degree per second. On the next line, we wait for the ramp to end. Before continuing to increase the substrate temperature, on line 13, we use the ramp command to open the arsenic valve controller to 50% at 10% per second. Right after, we open the arsenic shutter. Next, we set a waiting time for 10 seconds as the arsenic reaches its target flux. Now that we are supplying sufficient arsenic, we can safely heat the substrate to 600 degrees to remove the oxide. We start this ramp on line 18 at 1 degree per second. Then, on the next line, we wait for all ramps to end. When the wait ramp end command is called with our parameter, it waits for all ramps to end. This means that the gallium 1 cell and sample temperature ramps will both complete before the next line is executed. On line 22, we wait 5 minutes for the oxide to fully dissolve. And now we are ready to grow our sample. On line 25, we open the gallium 1 cell shutter and growth begins. Remember, the arsenic shutter has been open since line 14. We then wait just over 30 minutes to grow 250 nanometers of gallium arsenide. On line 17, we close the gallium 1 cell shutter and growth ends. The final steps are annealing the sample for 5 minutes on line 29 to allow the surface to settle and the overall smoothness to improve. Then we safely ramp the sample back down to 400 degrees at 1 degree per second on line 32. We wait for the ramp to end. And then we close the arsenic valve and then the shutter. And finally, ramp down to the transfer temperature of 100 degrees Celsius at 1 degree per second. And our recipe is finally complete. Thank you for watching. See you on the next video.